Welcome to our presentation, Building a Country on Open Source. My name is Jeff Ganender, and this is JavaOne13. What we're here to talk about today is how we helped introduce open source and Java scalable architecture to a country that was hell-bent on staying with commercialized software. And we're going to talk about some of the history of what occurred, and then we're going to talk about what we built, our architecture, some code snippets that we put in there, and how we made a very scalable solution. This presentation is all about scalable Java and scalable open source. I'm going to try to rip through the beginning here pretty quickly for the history to kind of give you an overview of what we've got, because I don't want to dwell on that. You're all here to kind of see the real technical issues, but I want to kind of give a little bit of history of the problem so you all kind of know what's going on and what we had to do. So first of all, let me just introduce ourselves. I'm Jeff Ganender. This is JavaOne13. We're from the Denver area. I do a lot of stuff with Java. This is my token marketing page here where I'm founder of Savoir Technologies. We do a lot of Java-based SOA consulting, and in particular with the Apache stack. As you can see here, I do a lot of stuff with Apache. But enough about me. That really doesn't matter too much, except that I do have a hobby as for not being a geek. I'm a firefighter for my for my community up in Evergreen, and so that's how I get a lot of fun. And Johan loves tattoos. He's got a good tattoo of himself on his wife's arm. This is a snapshot of him doing that. Come on, guys, help me out here. He also works for Savoir Technologies. He just authored a book, and just to let you know, it's OSGI Starter. A lot of stuff we do is with OSGI. We have several books we're going to give away for good questions. So if you give good, solid questions, you might get yourself a free book. It's been autographed by Johan and the other author, Jamie, who's sitting in the back as well. He's also a committer on a couple of Apache projects. And one interesting thing, non-geek stuff about Johan is he's a foodie. He is a great chef. He's a sous vide cook. These are pictures of some of the things that he does. Follow him on Google+. You will not believe the creations he makes. He actually has been offered jobs as a chef from his Google+ posts. I'm not kidding you. So
it doesn't pay well enough.
Yeah, that's how it works. Okay, so let's go from Denver. Let's fly down to South America to a country called Ecuador. Ecuador is an awesome country in South America. It's got 16 million people, or so they think they got 16 million. Sometimes they say there's 40 million. They don't really know. It's somewhere in between, but their unofficial count is 16 million. They're based on the U.S. dollar, which makes it easy when we go down there. That's kind of nice. And it's also a democratic nation. They have a president. They kind of have legislative bodies, so it's kind of got a similar setup to the United States. There's two major cities in Ecuador. There's Quito and Guayaquil. Guayaquil is the biggest one, and Quito is the second biggest one. Quito is up at 10,000 feet, and it's just a beautiful place. Something about Quito is they have many different government entities that control the IT. There's civil registration, police, business registration. So there's 12 entities there's more than 12, but these are the 12 that we worked with in Quito, and they all have different pieces of information that track individuals and businesses. So what they wanted to do was create what we call data seguro. So what is data seguro? Does anybody here speak Spanish? What is data seguro?
Secure data.
Hey, there we go. Secure data, that's right. They wanted to create a system that allowed access securely to the internal infrastructure. So everything in Ecuador is very similar through a lot of Latin nations of what's called a cedula. A cedula is like a social security number. So if you want a driver's license or something along those lines, you need to have your social security number, or in Ecuador, a cedula. And once you get a cedula, you get one of these. You get a really cool card with your cedula number on there. This is Julian Assange, Ecuadorian. He's still in London. This is his card. I don't think that's his cedula number. That was a joke. Come on, guys. But this is the same thing. This is the equivalent of a social security card. You need to use this to be able to get driver's license and that sort of stuff. So what's the goal? The goal of the government was to take all of these different entities, which are based upon cedulas, everything. It's kind of like a business has a federal tax ID number, and we have social security numbers. At the end of the day, they're all 9-digit numbers. They identify either a business or a person. Cedula is the same thing. So these entities kind of represent an individual or a business. What they want to do is make it so their citizens, or ciudadanos, I think I pronounced that correctly, have access to these products, so to speak. So to give you a little bit of history of what's going on, Rafael Correa, he is the president of Ecuador, and in 2007 he produced a message to the people saying that he wants everything to go on open source. So he put it up on YouTube, they broadcast it on the TV and say, we want open source because that's going to be where we want to go. And interesting enough, I think, Johan, you had a comment about maybe you had foresight of wanting to go to open source because of...
Well, we've had a lot of announcements around NSA, backdoors, everything else, and throughout South America, there's been a big push to get away from vendors, get into open source solutions. And if you look at places like Brazil, they will even push open source in the universities, pushing that out so that you actually have branches where people only do open source, try to get into it, try to learn code. And they're seeing benefits from it, major benefits, because they can focus the money on developers and skilled resources as opposed to licensing.
So maybe they knew something that we didn't know at the time. At any rate, let's go back. Oh, I got to move this. There we go. So basically what he said is, he said that they want to be the producers of technology and not simple consumers. They want to own the source code. They wanted to go into open source. And that bottom part, he really says there, and I'll read it because this really hits home for a lot of South America, is that for everyone must use free software. The Ecuadorian government has already established this is a governmental and state policy. This will be an important step in the integration of, why not say the liberation of Latin America. They saw what Brazil did. Anyone here from Brazil? Nobody? They saw what Brazil did, and they said, we want to go that direction. So what they did is they created this system called Data Seguro. You can actually go there on the web, dataseguro.gov.ec. But the question was, did they trust open source? Well, to be fully honest, nobody got fired for buying Microsoft. They went out and they built this whole thing on Microsoft. So they built a version 1.0, and what they did was they created the initial version of Data Seguro, which was a web.NET application, and it was connected to all these different entities over the net via SOAP web services. Did they have problems? Of course they had problems. First, we have the elephant in the room. They were told to go to open source, but they didn't. So they went with Microsoft, and everybody wanted to use Microsoft, but everyone had to be quiet and say, we want to go towards open source, but that didn't really happen. So another problem they had was licensing, licencia. Problem is that cost big bucks. That cost them a lot of money to license all that Microsoft product that was out there, SQL Server, the .NET stuff. All that stuff was costing money. And then they had inseguridad, or insecurity, so to speak. What hit the front page in El Comercio back in 2012 was a citizen was arrested, and this is directly converted from Spanish. I figure most of you don't speak Spanish, so it looks a little funky. But basically, a citizen was arrested for doing a data breach on this Data Seguro system. He was able to act as the president, get a cedula, and pull all this information out. President caught wind of it, and he finally said, hey, let this guy out and put all my data out there, because this is how insecure it is when we're using these products. I want it to be secure. The other problem they had was the architecture. The architecture is basically a web-based system, .NET, and it was point-to-point to SOAP web services on the back end. The problem was it was point-to-point. There was no message guarantees. There was no failover capabilities. The infrastructure was completely unstable. It wasn't modular at all. They weren't able to deploy on demand when they needed it. So they ran into a lot of problems. I mean, they would absolutely go to these websites and they would try to get their data and they couldn't get it. Nothing would come up. So they needed a scalable solution. And the first thing they started to look at was open source. Okay, look, we already told the people we want open source, we need to go for open source. What did that really mean for Microsoft? That meant bye-bye Microsoft, it's going away. And they said, let's go to Java. They saw Brazil bought the farm on Java. They did well with it. They said, there's a lot of great stuff out there. We're going to go with Java. And we're going to go with the Apache stack. We're tired of being held hostage to a particular vendor. We want to go to something that's open source. So they went with Apache Service Mix, which is an enterprise service bus. Total ESB. Who's heard of Service Mix? Great. They used Carafe, which is basically the OSGI container that allows for modular deployments and allows for division of labor. We're able to set up different Carafe Service Mix entities and deploy modules into them and basically put commonality between them and also allow them to scale together. We used ActiveMQ for guaranteed messaging and communication. We used it for persistent messaging, and we used it for event consumer-based polling. In other words, that's what got rid of the point-to-point. A consumer didn't need to know where anything else was. So it was nice to have consumer-based polled architecture, and it completely removes the point-to-point. This is the main backbone. We used Apache Camel. Apache Camel was data and communication routing. We were able to transform data from one type to another. And it was the container of all our endpoints. These were the main components of our modules that we would deploy. We're going to show you these in just a moment. We used Apache CXF to be the web service container, and we also used it to be able to use JAX-WS and SOAP for external communication and JAX-RS for internal ESB communication, kind of lighten the load, so to speak. And then we used Apache Cassandra. Apache Cassandra allows us to put together fault-tolerant data and a fault-tolerant system. And we basically used Cassandra as a cache for service queries to be able to back up for when services are down. And it's kind of cool. We'll show you more on that. So let's talk about the solution we came up with. We went down there and we partnered with a company called Latnus, which is an IT consulting company down there. American companies have a difficult time doing business directly with the Ecuadorian government. Typically, there needs to be a partner who's there. So they reached out to us and said, would you help build it? We know you're Apache guys. We know you're service-oriented architecture guys. Can you do that? And they introduced us into the Dirección Nacional de Registro de Datos Públicos, or DANERDAP for short. They were in charge of putting together this new data seguro and putting everything together and making it so they all goes through this ESB. So we built this system called SINERDAP, or Sistema Nacional de Datos Públicos. So we call it SINERDAP for short. It's much easier. And essentially what we built was something along these lines. We have 3 tiers here. We have a web tier that we use LifeRay. We have a routing tier that is an ESB, and we have an adapter tier, which are the ESB endpoints. These are 3 different locations that live in 3 different data centers altogether and multiple data centers within. But throughout the rest of this talk, try to keep in mind that we have 3 different areas that we're going to concentrate on for where we did our development, our deployment, and our architecture. Any questions? Yes? Where did we have the most problems? As far as scale, so we really didn't have problems with scalability per se. It scaled well, and you're going to see what we did in order to achieve scalability and fault tolerance. But our biggest problem we had was the adapter tier was what talked to the legacy systems, and these components lived on the adapter tier or near those, and the infrastructure was such that these systems would go down. And when they would go down, our adapters would kind of go down, and then we couldn't communicate. So we thought, how do we get around that? Well, we're going to use Cassandra, and you'll see what we did in order to get around that.
I think the biggest hassle we had was defining the contract between legacy implementation, pulling that data out, and converting it. And it took a long time before we got the government side to side with us, to say, this is the old, we'll bring it in, convert the data, we'll make it uniform. But that was also one of the key patterns in making this scale.
Okay. So let's talk about the web tier first. So the web tier, this is kind of standard stuff. They basically built a LifeRay portal for the front end. And the whole idea about the web tier was for your end user to do registration, to sign in, to log in with the cedulas, and get the data access. This is the centralized point that people would utilize to be able to access all of their data. And the whole goal here was to bring all this data together for them to see in one place. So what it ended up looking like was kind of from a really high level. And what we're going to do here is we're going to start at the high level and we're going to kind of drill in so you kind of see what we did. So from a high level here on the web side, we basically used a front end of an Apache HTTPD server. It communicated AJP to LifeRay. For security, it used LDAP. And then the LifeRay would communicate via JAX-RS using JSON RESTful service calls using the CXF clients. And that would communicate with the ESB root layer. So it would do stateless communication with the ESB. So a lot of people say, okay, well, how do I scale this in the beginning? So I'll kind of show you the physical layer and how that works. Physical layout was that we would have the Apache servers would have load balancers in front of them. So if anything happened to a data center would drop, the load balancers would be able to move you around to the different data centers. That was like the final backup of what would go. Then we had multiple HTTPD servers talking to multiple LifeRays, and it used AJP, ModJK sticky sessions and session clustering to be able to communicate with the LifeRay. And then LifeRay would communicate with the routes behind the scenes using RESTful services. Interesting thing to note is we use the CXF client not only because that's one of my babies that I get to work on, but also because it has some really cool capabilities to be able to fail over on JAX-RS communication. So if you're doing stateless communication with a service and it fails, you can have it automatically fail over to a secondary server or a secondary ESB and try to hunt down a service that's alive to be able to connect to. And you don't have to do anything else. You just set up the failover on it. You don't have to write any code like you have to do with some of the other RESTful clients that are out there.
But an important thing here is that this layer here, we're completely stateless. All the state is kept in the LifeRay container. There may be a token going, but we don't push state into the routing layer. That way we can scale this.
So the session clustering was across data centers or just?
Yes.
The session clustering was across this, but not in between data centers. So the data centers would have multiple servers in them, and you'd fail over. The only time you would ever have a situation where you'd lose your session is if you had to fall over to another data center. It's just too costly and too much latency to be able to push sessions across data centers. But within data centers, you were fine. What it meant for the client was it was very rare to lose a whole data center. So things worked pretty good, but if anything did happen, they always had a backup to go to, and they might end up losing their session. But it was rare enough that it wasn't worth the headache or the latency to try to push session clustering across.
How did you manage the new versions?
I'm sorry?
How did you manage new versions?
Manage new versions?
Yes, when you needed to upgrade that security patch.
We haven't gotten to that point yet. I mean, it's been running since March, I think. And we haven't had to upgrade the Apaches. So, I mean...
We've upgraded 2 or 3 releases, but since this is built on OSGI, it's a rolling deployment. So they have never taken it down.
Which we'll show you in a moment. It's had almost 100% uptime. It hasn't gone down, and you'll see when we get into that. We're about to show you that stuff. All right, so this is the routes tier, which is where that stuff lives on that question you just asked. So the routes tier, it could be a completely different data center, different area, different racks, depending upon how they want to put this stuff together. And the routing tier of the ESB is kind of the main conduit for the request. It's going to do all the mediation between the web tier and the adapter tier. This is all of our routing. And this is also what will handle the guaranteed messaging, so we don't lose messages. Yes, question?
Which application server did you use for LifeRay?
Oh, Tomcat. So let's see what this looked like. So what we had here was multiple service mix and none of these were on the same machine. The whole idea about fault tolerance is being sure that we have multiple ESBs out there. And what it would do is it would connect to ActiveMQ and would network of brokers that might even cross data centers or cross racks in a network of brokers to be able to communicate between different service mixes. What we're able to do is be able to deploy similar modules in different service mixes to be able to create failover. If we lose a service mix, the consumers on another service mix could easily pick up and take over, or they could share the load of similar routes. What that does is that makes a much more refined use of the processes, of the resources, and it creates failover. There's no single point of failure as long as we have similar consumers spread out between different service mixes. This component basically, the service mixes would take inbound JAX-RS calls. It would mediate the routes. It would go out and make calls to the via JAX-WS out to the adapters to gather the information, pull that information back, and essentially store the answers in Cassandra. And there's a reason we stored the answers in Cassandra was because if the adapters were down, we would go to Cassandra and say, I'm looking up this cedula for this piece of information. Do you have it? And the Cassandra service would come back and say, yeah, here it is. It's all yours. Yes?
Sorry, I presume your ActiveMQ messaging layer is for writes, or is it for reads as well?
It's for reads and writes.
It's read and write. The whole system and the whole key to scaling something like this is that here you have a synchronous call between your client and Liferay and Tomcat. Everything else here is asynchronous.
So since it's a read, you want to respond synchronously, right? So I'm wondering...
What you're doing is you're simulating. Think of a servlet request. You have a servlet request, servlet response. Put that on a queue. You got to deal with a timeout, but you can supply a response. So the whole idea is that we're taking one web server, putting the request out. There can be thousands of answering services that will provide you with a response.
And in ActiveMQ, you can do request reply using temporary queue. So a client can go and say, I'm sending this, here's the name of my queue, I'm expecting a response. And it's all asynchronous, and the client can wait for a response. And it's still very asynchronous in nature. And we'll show you a little bit about that. Right now we're at the 100,000-foot view. Well, we're at the 50,000-foot view. We're going to dive in deeper on this stuff. Yes?
What's the question concerning the architecture you have here? Did you utilize any load balancers from services?
We did, on the service mix side, we did not. What we did do is we had several service, well, let me state that. There were VIPs. So there were VIPs that would handle load balancing to a certain degree for what would come in. The answer is yes. F5 load balancers and VIPs. So the answer is yes. We had to do that. Otherwise, it made no sense to be able to cluster that stuff, especially the JAX-RS. I'm sorry, say that again. No, so there were no sessions. They're stateless. So our JAX-RS is stateless. When they went to log in and there were any credentials, it would pass the credentials along. So we wanted to keep it stateless for this reason. We wanted to make it that they could fire up another service mix without any impact on, and basically become a part of working without having to worry about clustering from that perspective. So
the way this is designed, it can run on one machine, it can run on 100 machines. And where we put them, how we load balance and so on, we'll get to. But basically, we can scale this indefinitely because there's no state.
And you'll see that as we drill down into this further. And then the Cassandra, anytime we got a response that came back, if you want to point towards it, Johan, every time we got a response that came back from JAX-WS, we would put the response in Cassandra. We'd also do it when we got updates. If they updated the database, for some reason, new information, there would be a call, a JAX-RS call that would come back, and it would update Cassandra directly. And we'll show you these routes in just a moment. Third tier is the adapter tier. These are the adapters. They live in the locations that are very close to the legacy systems. And these ESB endpoints, basically, they would translate the requests and proxy them into the back-end legacy systems, like what kind of service it was communicating with. Was it database or was it a SOAP service? Basically, it did all the communication, and it adapted a response that would work within the ESB and all the way back to the web. So these lived very close to the legacy systems. What did these look like? We got the calls that came in from the JAX-WS. It would talk to service mix. We had an active MQ master and slave for updates. And what that did was, if we could not communicate back with the ESB because of the infrastructure, we would load that information onto ActiveMQ, and it would those messages would sit there until, and it would do a retry, every 15 seconds, to try to communicate back to the ESB and say, I have an update for you.
It's configurable, and what we use this one for here is guaranteed message delivery. So anything that we requested or anything that they're pushing up to us is guaranteed to go through, as long as we have this. And this, same as this core solution, can be expanded. But this was more or less our set-top box integrating to whatever agency we're dealing with. It could have been Oracle, Postgres, Sybase, MySQL, PHP services. We don't care. We just write the adapter layer to get it into our format.
And so we would talk to back-end database systems using JPA. And we'll show you some code snippets in a bit on how we did that. Or we would use JAX-WS to talk to back-end SOAP services. And when we had SOAP RPC, we had to write very specific low-level code to be able to communicate with that. They actually had some old Microsoft SOAP RPC stuff that is completely deprecated, and that was very difficult to do. So we had to adapt and translate that into JAX-WS, pull out the XML payloads, and be able to send that back to the clients. Okay, so let's talk about service mix. How do we use service mix basically in the whole system? Service mix utilizes Apache Carafe. We leverage the OSGI container pretty heavily because we wanted modularity. We wanted to deploy things how we wanted to without having to bring down servers. And we used Apache Camel and CXF as our bundles with our routes. So what does service mix look like? For those of you who don't know, service mix basically is Apache Carafe for all intents and purposes. It allows shell login. It does all the management and utilizes Apache Felix as an OSGI container. And we use the Apache Camel and Apache CXF bundles in there, and we wrote Camel routes and web services. This gives us modularity. These are our deployables. We can deploy our Camel routes and our web services on any service mix container that we want. And this allows us to do competing consumers, essentially clustering service mix engines, service mix routes. This is kind of the magic of everything. So we'll talk a little bit now about what happens with Camel routes. The Camel routes we'll talk about first is those within the routes tier, the Camel routes that live within the service mix. So in the Apache Camel used for the routing tier, its main use was to basically mediate the JAX-RS calls and be sure that the calls went through. And even if the adapter failed, when it had to communicate with the adapter, we needed to handle that and give them some data some way or another, which is where Cassandra came in. And here's the route. So Johan, go ahead.
So here's UML markup for those that like it or dislike it, but it's actually useful in representing this. We would get a HTTP request that's sitting on Liferay, returning that into a JAX-RS after authentication. Everything has been done. We look at that when we get it in. We do a data check. So we check this cedula, we check the token, we check everything. Then we try and go out to the adapter and request an update on this cedula. If we get the update, we say, perfect. We wiretap that response down to Cassandra. If we don't have the data, if we don't get a response, we go to Cassandra, pick out the data. We then wiretap this, put it on an update queue. That's the whole asynchronous part. So what we're doing is we're saying, this adapter here is controlled in a proxy. So we can say during that synchronous call, are we allowed to ask this question? Are we going to get a response? If we don't get a response, go directly to Cassandra. That meant that they could prep the system, they could pre-fill the system. We're still not the data owners in this for a lot of political reasons. We deliver the data much faster than any of the agencies because we picked different technologies. If this call went through in a live system, you were looking at maybe 450 milliseconds. When it failed, we're looking at 75 milliseconds. So
actually, it went down as low as 20 milliseconds, and that's how we knew when the system got really fast. That's how we knew that there was failure on the adapters because it ran faster.
Yes.
So is it not strange? Usually, you first use the cache and then go to the actual source. If the data is not there in the cache, you're doing it the reverse. You first go to the source.
This has nothing to do with technology. It has to do with politics.
So
they are the data owners.
Your point is correct. We said, why don't you cache everything? The reason is the most up-to-date data is going to be on the adapters. So what they do is they try to they're pushing stale data over to the caches. The whole idea here was to make it so it fixes the infrastructure. If they had to push all the data over to Cassandra, then what you're saying is absolutely correct, and it's the way to do it. But like Johan said, it was a political decision that they wanted the freshest data at any given moment. They wanted to go to the adapter. So that is what we use Cassandra basically as infrastructure's down, we're giving you what we know.
How did you manage the data integrity problems?
Somebody did that. All right, sorry. Go ahead.
How did you manage the data integrity problems? So there was no data available in Cassandra.
Right.
How did you manage that?
We'll show you.
We'll show you some code. Yeah.
Yes.
So the data owners, were they asked not to change schema or anything?
Here, this was difficult because this could have been outsourced. It could have been licensed agency. It could have been anything. And on a strict time frame, we were basically, so we've been given database access, we've been given views, we've been given SOAP services and so on. Then what we did was we forced the government people to help us define this contract. That's why we picked SOAP, because then at least we could compile the entities and say, here's the new way. Yes?
Were you ever given a very legacy backend with a socket-based interface where you have to maybe like JCA, like the source adapters?
Luckily not. I've been given that in Brazil for credit card information. You can do it, but it sucks.
But we did have to write low-level SOAP, RPC, XML, raw XML, because we couldn't, JaxWS pukes on SOAP RPC. It's like, no way. So we did have to do some, for a couple of them, we had to do some magic. We had to do some magic adapting. So.
Okay, just getting back to your point, the area that sucks is the JCA, the Java Connector architecture, or just the process of writing that, or?
No, when it comes down to the writing the interfaces, doing anything like RMI or connector,
Right.
because there are, if you take SOAP,
Yeah.
it's at least more standardized. You have more people understanding it, and like any outsourcing thing, half the discussion, or if you take EDI, is finding the person you can talk to on the other side, who actually knows how his system works, and everything else. The second route, oops,
Sorry.
the second route here is just the update. That's another asynchronous. That's picking up the cedula information that came in from the wiretap, puts that down into Cassandra. We used quorum on these writes with the anticipation that if you were requesting something, you were most likely going to be on the same cedula, same servers. So eventual consistency worked out really well for us. And you write blazingly fast with this. And then we have, so this is the route. Route 1 and 2 are used from the web client. Route 3 here is used from the agency to push information back up into the complex. But the components are reusable, so we're putting the same thing onto the update queue, asynchronously updating the databases, off we go. And a large chunk of the scalability and building this was to find the right patterns. So every agency looks, smells, is the same to us. We're only changing types that we're storing for a service call. Here is where we had to do some integration work, but everything else is reusable and looks the same.
Okay, so real quickly, who here's familiar with Camel?
Yay.
Good, excellent. So basically, for those who aren't, this is what we call a Camel exchange. It looks kind of like JMS almost. That this is what a Camel message looks like. You get an exchange. It's got some headers on it. Then it contains a message. The message has some headers, and then there's a message body. This is what really goes through this entire system. So all the payloads, all the requests, XML payloads, when we're doing the translation, we'll convert it to XML or JSON, and those are the payloads that kind of move through the system. So these routes here, if you're interested in what this looks like, this nice little pretty graphic, it's going to look like this. Hopefully you can see that. We can. This is what the Camel routes look like. This is exactly, we pulled these routes out of our code that we're utilizing. We removed the passwords, especially with the Policia. The Policia is funny. They actually let us play with real data. So we'd pull people's, guys we were working with, and said, let's see if you've got a record. But what was cool is I could pop in my passport number, my American passport number. I could see all the entries and exits. I'm like, oh, man, they really let you play with this stuff. This is cool. Yes?
Any reason why you chose the XML to use that?
We used both. We used both. There's, so the reason why I like to use the XML stuff is for unit testing. It's just kind of easier for me. He likes to use the Java, so when you looked at our code, you'd see both sides of it being done. You'd see his routes were Java and mine were XML. We just mixed and matched.
I'll go out on a limb and say I passionately hate XML.
Yeah, he hates it. So, all right. So the RESTful processors, basically, Johan implemented the coolest thing. It was a service pool that would talk to the adapters. There's a lot of overhead in creating services. And what we see in a lot of software development is people creating CXF client services or Metro services over and over and over. And you get just a tremendous amount of garbage collection, a lot of time and overhead. So he wrote this really cool code that creates a service pool, and if the adapter was down, it was referenced in Cassandra. So let's take a look at that. We'll look at this code. I'll zoom in.
So the first thing we do here is that we basically have a commons pooling service pool where we're hiding our web services inside of a proxy. So we're calling those ones basically with reflection on the proxy. That way, inside of the proxy, I can say I have enough service clients. I haven't timed out. I can mark a service as dirty. That way I get the instant cutoff. We don't have timeouts anymore. We will have one timeout. The first client who gets a timeout to an agency, we mark that damn agency down. We don't allow any traffic. And we start pulling data from Cassandra.
Fluke, right?
Sorry?
Could be a fluke. Just a one-time.
Even if it's a fluke, what we found is just by marking it, when you have had a timeout, we give their end some time to revive everything. If they came back up, they'll go off and sit there.
So we might give a 5-minute. We had a configurable time limit depending upon the service and say like 5 minutes timeout. So it's marked as down and pulls everything, and that's what this code is doing in here. It checks, and it comes from Cassandra for 5 minutes. At the end of the 5 minutes, it marks it up, and the next client who goes gets it, and everyone who follows goes as well.
Then we have in red here the other question. What we're looking for is if we're timed out or we get a null response, the proxy will actually return a null if it's chopping off. We pull the data out of Cassandra. If we can't find the data in Cassandra, we finally throw a 404. And this was the contract they agreed to. We then stop the route and say that we can't update anything. But this is equivalent. So what we ended up doing is this, which I probably should commit back to Camel. Our endpoint that we're calling is completely controllable. So we can cut off the web service, we can time it out, we can mark it dirty, and we can reuse the same processor code from Camel over and over for every processor. We just change the types. Think of it as a generic DAO pattern. This is a generic web service pattern.
And you notice we checked out the service in the beginning, and here's the check back in. We used Commons Pool to be able to pool these services, and it works real well. So we would have all these services ready to go, and it would pool them, and it was wicked fast.
Another scalability trick hidden inside of here is that everything we're running on JAX-B. We made a JAX-B container that we have all types in. Every type conversion is done from the same OSGI service. So even if you have an object graph of a 700,000 to millions of JAX-B objects, if you instantiate once and pull that, marshallers and unmarshallers aren't thread safe, but you can pull them. That means that you can start reusing those. You can speed up XML marshalling. That's another common problem that you'll see in web services. You create, you recreate, you create, you recreate all of these context instances. All they do is bring up the object graph, process your request, then release everything, and you have garbage collection. We just keep everything floating.
And that's one of the magic of any high-load system. Reuse anything and everything you can. The more you do that, the more performance you'll get out of your systems.
Under load, you should literally have, if you look at JVisual VM, you should have like a straight load graph. You shouldn't see increases. If you start doing that, you are leaking somewhere or you're building and rebuilding.
Okay, so we took a look at the routes tier. Let's take a look at the adapter tier.
Jeff?
Yes.
So do you customize JXB marshalling and marshalling libraries, or?
We use normal, regular JAX-B. We just took the interfaces for JAX-B context, and
He pooled the context.
I pulled the context, and then I put a commons pool behind it.
And it's wicked fast. And the other thing that it does is it gets rid of the leaks. I don't know if you've ever experienced high load, JAX-B, reuse of the context. You end up with lots of leaks as you create and destroy your marshallers. By having the marshallers already created and pooled, we get no leaks at all. It cleans up after itself really nicely. So it's a good pattern to use in any high load system that does any type of marshalling. So the adapters, let's take a look at the adapter layer. So we use the Apache Camel adapters. Each company or government entity basically has its own adapter service to adapt its legacy system to what we want to see. As I said before, it lives very close in the data center for where the legacy systems are because it's an adapter. It's adapting their stuff to the way we want to see it, and then we communicate over the wire to our own stuff that's living remotely. We certainly don't want Oracle streams going over the net. So we'd rather make these adapters that work much better. And basically, it'll mediate between SOAP and any of the back-end company or government entity data syncs. So let's take a look and see what it looks like. Go ahead, Johan.
Fairly similar, where we have JAX-WS endpoint. This is our request from the ESB. We're calling with this one, we're going out to the legacy system. Whichever way we could, we pull in the data. This is where the code that you don't want to pass code review is sitting. This is, whatever it takes to get it in. We're converting it. We're putting it back, giving a SOAP reply. We have a second route where we have updates coming from the agency. They put an update that it's the same payload as the cedula. It's just a put update. We put that on a queue. We put that on an ActiveMQ update queue, which is the reverse of the ESB layer. Then we put that into a prepare update and retry update. So we knew that these adapters on the agency side were going to go down more. They could be behind DSL for updates. They could be behind a firewall or something like that. What we do is we take that payload, put it on a queue. We try and send it with the ActiveMQ. We basically have a processor that's doing the producer templating. If we can't send up on the JAX-RS, update the ESB, once again, we use the same technique. We mark that as dirty. Any updates that we have, we put on a retry queue. Then we put a timer in and say, let's see if we can send up now. If we can send, then we start draining with a slow, basically a thread sleep, so that you don't want to flood the central system, but you don't want to miss any updates. So what we're basically doing is we're slowing everything down as much as we humanly possibly can. And then we drain these systems. That way, this adapter is really only a reverse of the ESB route. The code is the same, the types are the same, the JAXB contexts are the same. We can reuse all the classes. That leaves us with this implementation class here.
Okay.
And that's our introduction. Yeah.
No, so I was just going to say, so one of the things we had to do is we had to talk to a database. So we used JPA for the most part. JPA was the way to go. We also needed rapid development, which is why we used JPA. And we used generics for CRUD. In other words, we didn't want to rewrite this stuff. So we used a really cool pattern for our JPA. So this is what we call our generic DAO. I don't know if you can read it. If not, I can zoom in. But basically, this is a generic DAO interface that uses generics here. And we basically have create, read, update, and deletes on these. Pretty standard stuff. Let me go down here. And then what we did was we would implement it with a generic JPA DAO. So the generic JPA DAO basically set our entity manager and allowed us to do our general create, read, updates, and deletes. So now that we had that, we'd be able to implement this stuff by extending the generic JPA DAO. We declare what are the types, what is the type keys, what is the return type supposed to be on it. And if you take a look at this, just by declaring a DAO in this fashion, I have full create, read, update, delete, and then I can do specific getters if I want to in there. It's that simple. So we were able to do that. So for 10 of the entities or 8 of the entities, we had to write this stuff and write pretty intricate stuff. This allowed us to knock that stuff out. This is a fantastic pattern to use for JPA. It gets rid of a lot of replicated code. You write it once, and it's this simple to implement. Okay, so we kind of looked at, we're back on the routes now. We want to take a look at what we did with Cassandra. So let's have a look at Cassandra. So Apache Cassandra is basically a NoSQL database. It's all Java-based. Who here's used Cassandra? Can I see hands? A few of you?
What clients do you use?
To connect to it. Anyone?
Anyone.
So there's a few libraries to do it. A lot of people, they'll use something like Hector, which works pretty well. Well, I'll get into that in a moment. But we wanted Cassandra to be there because it's fault tolerant. It mends itself. Its cross data center capabilities are just amazing, and there's no single point of failure, which is really nice. We really needed that, pretty huge. And talking about what clients did we use, well, this is kind of what Cassandra looked like. So you can make it so it scales well in a rack, between racks, and between data centers. So we were able to set these up to put priorities for where it's going to store its data based upon whether they're in the same rack, different racks, or different data centers. What it did was this really gave us a good, solid, fault-tolerant way of pushing our data and getting our answers back into Cassandra. When we were talking about the APIs, how do we do it? Cassandra, a lot of people use either Hector or the Netflix library or a Thrift API. I think they all kind of stink, to be honest with you. They're still extremely code intensive to use all the above. Thrift just sucks to use. No offense to the Thrift guys, but it's ugly code and it's a lot of code. And therefore, we need to do like what we did for JPA. So we needed an API that was easy to use for JPA for CRUD. We needed something similar to what I just showed you. So in a nutshell, Cassandra stores things in what we call, yes?
Sorry, quick question. Maybe you already mentioned
Yeah.
this. Did you attempt to deploy any of your components into the cloud, or did you have all your own data centers?
We actually did a lot of development in the cloud, and it worked just fine. But for the most part, when it went into the government, they wanted controlled data centers. Part of our development was using cloud and using GitHub and that sort of stuff, because we did a lot of development up here. We'd make a couple trips down there, but we were working with them purely through GitHub, which worked out real nice.
Their production stuff.
All the production stuff is in this data center, but this works for the cloud. This exact architecture would work absolutely fine in the cloud as long as you know where your stuff lives and you don't get those randomized dynamic IPs. This stuff works fine. So this is what a column family table looks like inside of Cassandra. We notice we have a row or a key, and then we have columns, and they're kind of randomized. One of the things we noticed was if we took a column family and kind of filled in all the columns, it was nothing but a Java bean. We could actually map a Java bean to this stuff easily. And even if we didn't have the columns, they would end up as null values. So it made it really easy. So we said, hey, let's just map the row and the column to fields in a Java bean. So we wrote this really cool API. What we did was we wanted to just use beans. So we would create entities. Some keys are called composite keys where you can have two fields together. So we created an annotation called a composite component, and we order them. So these two, for example, was Tipu and Cedula. They would make up the key. And that's called a composite key. So by adding these annotations on here, our annotation processor was able to mold those together behind the scenes and use reflection to be able to map this entity to a Cassandra to a Cassandra record, so to speak. So we created a generic DAO, kind of looks similar. You know, delete, get key, save, find, kind of some CRUD stuff that's in there. So we were able to do that. And then we wanted what was called a generic iterating DAO. We wanted to be able to use something like a result set. We didn't want to blow up memory. We wanted to be able to say, give me all the records that match this criteria. That could be 1 million records. Well, that would blow a JVM under normal conditions. So we wrote an iterator. So it has almost no memory footprint, and we can get as many records as we want by iterating through each one of the records. So we created this generic iterating DAO. Now, there's a lot of code we put behind it to handle this because it was all based on reflection. But in the end, it was this easy. In order to create a DAO for Cassandra, all you did was create an interface and an implementation of the generic iterating DAO or the generic DAO, and that's it. There's no code. You have full CRUD going in and out of Cassandra. How long did it take us to knock out the DAOs to Cassandra for each of these?
Well, I mean, we can take this story further. We have expanded on this library. We made sure we open sourced it to ourselves before because we realized this is going to be a home run. But in a project this type and scale, we can put people who have no Cassandra training, does not know what it is. They're type safe. We know what's going on. We control the type inferer. This is all the code you need to start storing things and retrieving things out of Cassandra. If you can think and solve your problems with a set map and a list, you're home free. We have the solution. And I think it took Jeff initially
A couple of weeks to write?
A couple of weeks to write the first one of this. We put people who had no other skills than being literally able to start Eclipse and said, copy paste this, put the type in, you're storing data to Cassandra. The other beauty of Cassandra as a NoSQL solution is that it's fully 100% Java, which means that it's really damn easy to unit test because you can embed this. You can run unit tests, you can run load testing, you can run all of these things in your IDE. It's not going to change the deployment.
There's a great product out there called, or open source product called Cassandra Unit that we used. So we would run Cassandra in your unit tests, and we could exercise all this stuff. We drop it in production. I think day one we dropped in production, it ran flawlessly. We were like, wow, no bugs. Unbelievable. So it worked
there's
really
no
nice.
bugs because we didn't write any code when you deal with
That's
the
exactly correct. There's no code, and that's the point. And this is the use. If I want to use it, I create a DAO, which is what you can see up here. And then this is an example iterator. I'm using my DAO to do a find, okay, in that middle line there. And then I just go through the iterator. I'm able to pull the columns and read the columns. It's that easy. If I'm just using a Java mapping bean, a general generic DAO, not even the iterator, look what's in blue. That's how easy it is. I'm pulling an OSGI service that I got from Spring or Blueprint. So I'm pulling in the DAO there. Look, there's my save. There I'm looking if there's a key. I'm doing a finding, doing a delete and a lookup. That's how easy it is. What's the good news? We're going to open source this library because it is so cool. And it's been so great to the people who've used it. They were just blown away how simple it was. We're going to open source it probably in the next few weeks. So everyone can have in the masses can utilize it. So it's something we're definitely get out there and y'all can use it. It's just a great library. So that was Cassandra. Our final component is ActiveMQ and how we used it. Basically, it's JMS. We used it for persistent messaging. We did not want to lose anything. Anything that went through the system, we wanted to be able to track it. It basically was the backbone that removed our point-to-point, and it implemented the consumer polling strategy. What that meant was all of our modules did not need to know who to connect to. It just needed to know where ActiveMQ was, and we could plug in any amount of end user routes. We could scale service mixes endlessly if we really needed to.
And if you think about it, we don't need UDDI, we don't need a registry, we don't need to know where services are. We can just build in a Lego fashion and start adding things in.
So ActiveMQ is the backbone. It is the bus. And how we set this up here is we had multiple data centers. Each data center had what we call a broker node. And that was set up as a master and a slave. So if the master goes down, the slave picks up immediately. And if both the master and the slaves go down, we fail over to the second data center. As you can see, the Camel component on the left there, it tries the master. Can't get it, goes to the slave. Can't get it, then it starts going over to the other data centers that are further away. Same thing with the one on the right. It goes to the closest data center, and it starts picking up. This is all done through what we call the failover transport. It automatically connects. There's no code. You use the failover transport in ActiveMQ. You can tell it where you want to do it, and you can do it in the order that you want it to connect. Or you could have it do it randomly if you wanted to. Each one of these data centers is what we call a network of broker node. We can scale massively horizontally by adding another broker node. If we want to scale up, we just add another node. It can be in the same data center. It can be in a different data center. We can scale massively and handle any type of load. The messages, the neat thing is the messages flow freely between the different brokers. So I could stick a consumer on any other broker and those messages will go across. So we're able to scale up and everyone can see the messages as they need to consume them. This also allows for consumer-based event handling. It basically means the endpoints, they do not need to know where others live. I can plug it into ActiveMQ anywhere. It'll consume messages that's meant for it to be able to do things by itself. And what that does is that loosely couples the producers and consumers. It allows us to do competing consumers, so you can share the workload based upon how many service mixes that have similar routes in them. So now I'm able to really scale by sharing the workload and passing around. One service mix may pick up one type of route, and another service mix may pick up a separate type. So that is kind of how all these components, all the different tiers of the system fit together. So what is the result of what happened? The result is we're able to handle over 40 million transactions per day. 40 million. We can handle up a lot more than that. When we were load testing it, it was amazing what we were pushing through this thing. We handled full failover. I think one of you asked a little earlier, where were the difficult points in failure? As you can see, we fixed everything. We kind of set it up where there really was no single point of failure for the most part, so we didn't have an issue, and that was the whole goal of what we wanted to do. What we did find was the Ecuadorian government loved the system. They found it was an immense success, and it was a tribute to Java and leveraging open source. It was probably one of their biggest success stories for a massive governmental nationwide implementation. It pretty much, it got rid of all their doubts, and it really made them get rid of, starting to get rid of, hate to say it, no offense to the Oracles of the world, and Microsoft getting rid of these licensed products. And it's become such a poster child that Chile, Peru, and Colombia have been looking at that system and said, wow, how can we reproduce this? This is fantastic. We want to do that too. It gets them out of vendor lock-in. It saves lots of money, and they know what's going through there. There's no back doors for our friends, the NSA, to read. I didn't say that. Yes?
The ActiveMQ layer that you just showed, I think passive is more kind of initially you guys have used. For this type of transaction, have you guys thought about how we can have two actives and two passives to kind of high availability instead of master slave? Have you guys thought about it?
Well, network of brokers kind of does that. So that'll give you some degree of high availability. It's not a true cluster because they have to communicate, but you kind of get a hybrid between that of the master slave really is pretty much if your machine drops, the other one's going to pick up and start going immediately with almost no downtime. Whereas a network of brokers, you're able to have two masters being able to communicate with each other and pass messages back and forth. That was our goal, was to be able to do that. So we kind of did a little bit of both.
And how much file you pushed on the transactions per second?
Load testing?
Load testing, I think we load tested a single service mix was able to get 200 transactions per second.
No, I'm talking about the ActiveMQ.
That we didn't measure that, but since it was going over to ActiveMQ, clearly minimum of 200 per second per service mix talking to ActiveMQ, and that was going to several reads and writes. Remember, these were small payloads too, so we were able to get very, very high load through there. We've gotten up to 30,000 per second in a network of brokers, on ActiveMQ with very small payloads, and we've really pushed it. If you have to tune it, you're not going to run that out of the box that way. And the last point, the system's success enabled other Ecuadorian government further build out applications built on Java and open source. It was a raging success. And from that, this is kind of like the poster child of a raging success of deploying something like this in the government, unseating a commercial vendor and getting comfortable with Java and open source to say, this is some of the best software we've ever had and seen, and it all had to do with Java. And that's what this is all about. And I really hope that some of our techniques here, some of the things that we showed was helpful. And we do have questions, and we're going to start handing out books to good questions. You've had your...
How long did it take?
How long was it? About 6 months?
6 months for the first iteration. Then I think they...
How many people?
Let's put it this way. The first adapter, it probably took 3 weeks. And writing the Cassandra library, writing the proxy code, handling all of those ones, the last one I did at the airport in 4 hours because I knew exactly what to copy paste. And so it's all about finding patterns you can reuse.
Hand that man a book.
Well, I'm going to take this off.
Because Cassandra is Java-based. It also has one of the highest throughputs. I think there was a really good throughput view on Cassandra on as you add on the nodes, the amount of throughput you can get on it, and I think it just smeared everybody. The decentralized capabilities of it that it has was pretty good. The fact that it was Java-based, it made unit testing really, really simple. We didn't want to have to sit there and run another entity. It worked real well, and the way it just merges and replicates itself is just fantastic, and that's really why we chose it. Give this man a book. One moment. He had his hand up. Go ahead. Say that again. We logged everything that went through. We used logging with the log4j, and then they would use Splunk to be able to analyze that data. So we knew what IP addresses came through, what was the cedulas that was requested, who did it, when, what systems. So we would log all that stuff. That was some of the stuff that came out of that security problem. Was we didn't want that happening again. In fact, we wrote caching LDAP adapters. Is what we did. Give that man a book.
Who? No, what? Where?
In the white hat.
Here we go.
The architecture itself would be reusable. Obviously, the back-end adapters would not be. Also, their security mechanisms would have to change, but for all intents and purposes, this could work directly in Peru, yeah. And I think that's why they're looking at it. Absolutely.
This is, let's put it this way, it's computationally the problem we have with databases today is that we forget about the fact that we normally have a natural key, throw that natural key away, get a generated key, and rely on that. Any problem you have, when you keep the natural key, you can solve it this way.
Let's go over here. Yep. I'm sorry? So there's a Camel test that there's a Camel test framework that we can utilize, that we can put in there different types of mocks to work with the data and make it look like how it's supposed to speak. So when we would piece them together, obviously we had integration testing. However, we use Camel test, which allows to inject mocks in at different points, or to say, hey, did this go through with the Camel test? Let me know if this exchange, how many messages went through, and the end result message needs to look like this. So we unit tested all of our Camel routes heavily. Yeah. Yeah, absolutely, you could do that. And that's why we use stuff like Cassandra unit, and we would actually use that in line with Camel to say, hey, are we saving to Cassandra, and did I get data back? So that's how we would do that. We'd build like short little unit tests. Give this woman a book. Yes?
How much was actually spent on hardware for 40 million transactions? Do you have any idea?
I have no idea. We stay out of the hardware talks because the network side guys are a different breed of thinking and human beings.
It actually wasn't, the initial install isn't very expensive. It was off the shelf, I think Dell equipment, 12 gig machines tops.
The whole idea is we're scaling horizontally, so hardware's cheap. Yes?
You already answered this, but I still don't get it. What is the benefit of queuing read requests? Or are you using WebSockets kind of technology?
I even did...
Pick up your mic because they're recording.
If you do, I'll give you my business card, but I did a presentation at UberConf on this. The benefit is, if you think of an EE container, it's a monolithic synchronous call, right? Where you run out of processes is in how many threads you can maintain. And if creating the response is more expensive, what you can do is you can pre-pull, you can pre-compute, you can set up more response builders, allowing you to, one, field it across more data centers. You could shard databases. You could replicate databases. All we're trying to do is to get the read as quickly as possible. People with PHP used to do things like creating memory tables in MySQL of things that came in to make it look like it's instantaneous. And if you think about it, this is very similar to PayPal, Google, whatever. You have a front-end farm that's disposable assets. Then how we build the response, that's the real workload.
So the library you built for Cassandra, are you still using Swift or Hector
underneath? Yes. So the iterator, that's a slice query. But what we wanted to eliminate was this whole by type infer, converting data. Now we can, based on reflection, say that this is a string, it's a number, it's this and that.
Sure.
Yes?
When a legacy system is down, you queue a writing request instead?
Yes.
But are you able to write this in the temporary Cassandra cache? Meanwhile?
We didn't really work with the temporary stuff. We just, when it was down, we let ActiveMQ and ensured that it got written to Cassandra, period,
Okay.
which is really what we did. So we used ActiveMQ as that. All right, for the book, one more question. You.
So while you are building this lot of copy-paste related stuff, so do you think of maybe externalize these copy-paste to make some configuration? So then you have to write the new code like this next time.
Yeah, actually, so we said on the new iteration, we're going to be going through a new iteration. We did a lot of copy-paste, but what we're going to do is something called a dynamic route factory, which is really what we're going to end up doing. So we have one type of component that we write. We fill in the blanks. There is no copy paste. We fill in a couple of class types and that sort of thing, and boom, it'll work the same. So our next iteration is going to have this dynamic route builder with a route factory, which is what ultimately we're going to do. And that had we gone down that route at first, we would have really knocked this out. But as you go down, it's kind of like you're trying to figure it out as you go. So give that man a book. You. That's a good question. Keep an eye out on the Savoir Tech, and we'll be tweeting about it. That's our Twitter handle is at Savoir Tech. We'll put it out there. We'll probably ASL it, Apache license it, and just check for it on GitHub, and it'll be out there. No, we don't have a name for it. We need to come up with one. So, but it's going to be cool. So anyone who does Cassandra work, we highly recommend it.
Yeah, and I added last week a couple of tweaks to it, so now I can actually handle dynamic columns. So I can handle maps and lists in this, because I had a use case where I needed to use our library, where I wanted to use our library, but we had customers who wanted to use CQL. And CQL or not, that's a whole different debate, but the customer is always right. That way I can make it so that they can look at the data types.
Yes?
How did you handle session clustering, session application?
Tomcat has session. It will handle the clustering inside of it. You can set up the clustering engine, and that does everything. So, but you need to set up your mod.jk to handle sticky sessions and be sure that you're talking to the same one. Otherwise, you get too much latency going in between the different clusters. And it's important to balance how many Tomcats you want together, because then you end up in a star network, and then you start getting more latency because they're all pushing the same cluster around. So, any other questions? No? Well, thank you very much. We appreciate it.